In this video, you're going to learn at a high level what Docker is and what you can use it for. Future videos will show you how to use Docker, as well as a deep dive into how Docker works. So what is Docker? In this section, we're going to answer some important questions. By the end of it, you should be able to answer what is a container, how is it different from a virtual machine, as well as being able to discuss the advantages of containers versus more traditional approaches for packaging and deploying your application. So a good first thing to understand at a high level is what is Docker for, and why do we need to learn it as developers? So Docker enables us to package our application, and you package it in a way that's agnostic of the technology inside. So what does that mean? Well, if you were to ship someone a jar file, then it's specific to Java. We don't ship Python applications inside jar files. But when we build and deploy a Docker image, there could be anything inside. The thing about these Docker images is we can version them. So like you'd version your jar files and your WAR files in the Java world, we're going to version our Docker images. And then we have the ability to ship them. It's a standardized way, a Docker image is a standardized way of being able to ship things from your development team or from your CI server onto production machines. And then of course that means we can use Docker as a mechanism for deploying. Now later in the course, we're going to be looking at Kubernetes in detail, and we're going to be using Kubernetes to deploy. And then the final step is of course to run the application. Before we jump into how Docker achieves all these things, let's see how we've been doing this in the Java ecosystem for many years. So if we go back a while, then we as developers, we used to build WAR and EAR files and then deploy them to JEE servers. Or with more modern frameworks, we've been building self-contained executable jars. So Spring Boot and Drop Wizard, for instance, they both allow you to build a jar with all of its dependencies in, and so you can just execute it with Java -jar. These are actually very practical, and more practical, I think, than WAR files and EAR files, because the only thing that you need to run it in production is a server with Java installed. However, there's a problem with both of these. And it's that the production side of your company, so your DevOps or your sysadmins or your operations team, they need to know how to configure Java. They need to either install Java or JEE servers, and they need to worry about things like memory settings. Whereas normally it's the developers who are experts in these things. And not to mention that you could end up running in production with a different version of Java than you've been testing with locally in your test environments or on your development machine. An alternative way of doing it is for development teams to know more about the production environment. So perhaps you could build dev files or RPM files. So a bit like Docker images, you can put anything inside these. But then what we've done is we've created the opposite problem. We've pushed operational concerns back to developers. Another aspect of traditional application deployment is whether we do multi-tenancy or not. So when we had JEE servers, of course, they're multi-tenant by design. We're deploying our same WAR file into the same JEE server, and it will be co-located. And that did present a lot of problems. But when we moved to executable jars, things like Spring Boot, then we had another problem. It was suddenly very hard to deploy more than one application on each host. So when we deploy application, we end up with a single server with a single Java processors running on. And if we deploy a new application, or we want to increase the capacity of an existing one, then we need to add more servers. Now this has two major downsides. The first is the provisioning lag. So how long does it take for us to get another server? If it's virtual, maybe it's just minutes, but if it's physical, we might need to wait days. And the second is utilization. So at any given time, many of the servers, many of the applications probably have quite low utilization. So maybe 10% on the first one and 20% on the last one. And underutilization, once you get to a certain scale, costs your company a fortune. And Docker is going to help us, and particularly containers are going to help us to solve this problem. Before we dive into containers, let's look at a more traditional answer for this problem, and that's to use virtual machines. Virtual machines allow us to run many operating systems on the same hardware. They do this by taking the resources of the hardware, say the CPUs and the memory, and virtualizing it to make it appear to be many smaller CPUs and memory. So for example, a production grade computer or server might have 128 cores and 256 gigabytes of RAM, but it could pretend to be 64 servers with, say, 2 cores and 4 gigabytes of RAM each. Well, how does this work? Well, we have the underlying hardware, then there's a bit of technology called a hypervisor, and that's the piece of software that can do the virtualization. Once we've got that, we can install lots of host operating systems or virtualized operating systems, and then we can run our Java application inside those operating systems. Each virtual machine will get its own IP, and from inside appears to be a normal server. And there's a big benefit to this. When we deploy our applications into virtual machines, we can treat them pretty much as if they're real servers. The mindset and the knowledge required to develop Java applications in virtual machines is very similar, if not the same, as developing on bare metal. But there are some downsides, and the biggest downside is efficiency. We are having an entire copy of the operating system potentially to run a very small Java service. It's wasteful. And in addition to that, it's quite hard to run the exact same setup locally on your desktop or on your workstation on your laptop. But when we move to containers, things improve a lot. Rather than using virtual machines, instead with Docker, we're going to use containers. So a container, on the other hand, allows you to run your application side by side on the same operating system. We don't have the overhead of virtualizing an operating system. They can run directly on hardware, so we don't actually need any virtual machines. We can actually install them directly, but we can also use them on virtual machines. So if you're running in Amazon or Google Cloud, that's also fine. And they're typically a lot more efficient than applications running inside virtual machines because it doesn't need to go through the hypervisor, the virtualization layer. So let's have a look at how these are structured. So imagine we had the same hardware as before, and then we have a real operating system on there. Now, typically that's going to be Linux. There are container-like things on other operating systems, such as Windows and Solaris, but the containers we're going to talk about, the ones that Docker is based on, are going to be all about Linux. And then on top of that, we have a container runtime. And then there are multiple container runtimes available, but we're going to use Docker. And then on top of that, we can run lots and lots of different applications. And in our example, we're going to run lots of Java applications. The container runtime doesn't quite sit in between. It's really just an interface to set up containers. And it does that by using lots and lots of great Linux features, which Docker has made easier to use. So we've used the word container quite a lot now, so it's about time that we define it. A container is an isolated group of processes that can use a limited amount of resources. The reason they need to be isolated is we're going to run them on the same operating system. My Java application could potentially be on the same machine as your Java application, and we don't want them to interfere with each other. I don't want my Java process to be able to see your Java process and vice versa. And then the resources is also important. If we're all going to run on the same machine, we need to make sure that one application can't use all of the CPU, say, or allocate lots of memory up front and then leave nothing for the other processes. So if a container is all about isolation and limiting, let's have a look at the most important parts of that. So we've already named a few, but let's go through them. First off, there's process isolation. When your container runs, it thinks it's in a full Linux distribution, but in fact, the only process it will see are the processes that are in the same container. And more often than not, that's going to be one Java process. And then there's the file system. As far as your container is concerned, it has a full Linux file system and potentially even somewhere to write. And every other container, even though they're working on the same machine, will have a separate copy. And we're going to see how Docker does that very efficiently. And then we've also got memory isolation and network isolation. It wouldn't be very good if everything we write to memory is visible by another process. Then on the other side, we've got resource limiting. So the most important to our CPU and memory. We won't want to be able to share the portions of the CPU out to different containers. And we'll spend a lot of time on CPU later in the course because it's one of the trickiest parts of running inside containers, especially with multi-threaded Java applications. For memory, we just want to sharely divide the memory between the processes. Of course, some containers will need more than others, and we need a way to be able to figure that. And then we've also got disk I/O and network. Just another note on network here. Network isolation is one of the things which makes it very easy for us to run multiple containers on the same host. We could have 6 different applications all built with Dropwizard, all trying to use port 8080. And if we're running inside a container, that's absolutely fine. But if we're running on the host directly, we'd need to allocate different ports to different applications. Now, all of the features for doing this isolation and limiting are built into Linux. What Docker does, and what we're going to see in this course, is that Docker makes them very easy to use. It means that I can do it in a few commands rather than a few hundred. If that is what a container is, then what exactly is Docker? Well, Docker is both a company and a set of technologies that that company builds, which make containers easy to use. And in this course, we're going to cover quite a few bits of technology that have been created by the Docker company. We've got Docker images. So that's the format which stores what's going to be in the container when it first starts. We're going to be building lots of Docker images with Java applications inside. The way you build a Docker image is with a Docker file. So that's a DSL for creating a Docker image. And then when you're ready to run it, then you take the image and then you can run it as a container. And where do you get the image from? How do you get the image to production? Typically via a Docker registry. So a registry is a place where you can store and version images and pull them down onto your production machines. Most of the companies that you work at will have private registries, but there's also a publicly available one called Docker Hub. Before we end this video, let's just summarize some of the benefits of using Docker and running containers. So the first big benefit of using Docker is that it makes using containers easy. We're going to show in the next video with a few commands how we can get going, build a Docker image with a Java application inside and run it very easily. Whereas if you do this with the Linux features that they utilize directly, you'd be writing hundreds of lines of shell script. And a big benefit of using containers in general is, whereas we're going to put Java inside it, it could be anything. So your company, and many companies are doing this right now, they're standardizing on Docker, because that means that they can have development teams putting Java inside there or Python, and their infrastructure can be agnostic to that. When it comes to multi-tenancy, containers are a complete game changer. They're much more efficient than using virtual machines, and they allow us as Java developers to program as if there's nothing else on the box. And another advantage over running virtual machines is that containers are easy to run locally. We're going to do this very soon, whereas if you've ever tried to run virtual machines locally, they're very resource hungry and error prone. And then finally, very important for you, is it's great for your CV. Most development jobs now are expecting some knowledge of Docker, so it's a great thing to be studying. So time's up for this video. Next up though, we're actually going to start building Docker images with Docker files. We're then going to run them as containers, and by the end of it, we'll have run our first Java program inside a container. So see you in the next video.